And this new principle is the so-called Huff transform, which was originally developed for image analysis. So what is the Huff transform? Well, it transforms each object, each point into a so-called parameter space, and this parameter space represents all possible subspaces that accommodates this object. Yeah. So basically, that are all possible hyperplanes through this point. Yeah. So we'll have a visualization of that right in a minute, and this parameter space is a so-called continuum of all those subspaces. And the good thing is that, well, of course, all those possible subspaces that go through one point, so just consider in a two-dimensional case, in a two-dimensional space, one point, so how many lines, different lines, go through this point? Well, an infinite number of lines, of course. Yeah, but the parameter space represents all of those lines, all of those subspaces, all of those hyperplanes by a considerably small number of parameters. That's the good news here. Yeah. So even though it's an infinite number of subspaces, those subspaces are this infinite set of subspaces are represented by a fixed number of parameters. Actually, for d-dimensional original feature spaces, we have d parameters in the parameter space, so the parameter space is also d-dimensional. Yeah, and this transformation is a generalization of the Huff transformation. The Huff transformation, as I said before, originally developed in image analysis for the detection of linear structures in images, for lines. That sounds good, yeah, and that's actually the idea why we used we use this Huff transform for correlation clustering now. So the Huff transform, well, check out the board, is a little bit hard, so I will give you another podcast here to explain the Huff transform in 2D, which is very easy actually. Yeah? So after you have watched the other podcast for the Huff transform, we know that, well, now the generalization to the d-dimensional stuff. Well, for each d-dimensional point, there's an infinite number of d minus one-dimensional hyperplanes going through P. Yeah? So, for example, in the two-dimensional case, take P2. We have an infinite number of lines through lines because d minus 1, two dimensions, 2 minus 1 is one-dimensional hyperplanes, so one-dimensional hyperplanes are lines. So through a two-dimensional points, there is an infinite number of one-dimensional lines going through. Yeah? And each of these hyperplanes, in that case lines, or each of these hyperplanes, S is defined by the point itself and the angles, yeah? Where the angles define the normal vector, which is this one here, normal vector. So this line here is defined by P, for example, and the normal vector. And the normal vector in not Cartesian coordinates, but spherical coordinates can be expressed by d minus 1 angles. Yeah? And now we can use this function here, the function that actually maps the d minus 1 angles to the distance of the line to the origin. Yeah? So the line is defined by P, and the normal vector, which is defined by the d minus 1 angles. In this two-dimensional case, it's just one angle. And then this line here has a unique distance to the origin. And that can be computed from P and the d minus 1 angles of the normal vector. Yeah? And this function is actually nothing else than the parameter space. So the parameter space maps the angles, in this case the one angle, to the distance from the origin. Yeah? So the parameter space plots the graph of this function here. And the property of this parameter space, or of this transformation, so this function is actually the transformation. So we transform each point into a function in the parameter space. So you see here, it looks like a sinusoidal curve, and we will have a look later why that is. So, so for example, fp1 here, this red line here, this is the graph of the function for p1, which is given here, and each of the points on this red line here represents one line which is going through p1. And all those, so the graph of this green one here is the graph of fp2 from above here for point p2. Yeah? So a point on this green line here represents a given line through p2. So all the green points here of this graph here, of this function, represent all possible lines through p2. Yeah? And you see here that these three graphs intersect at exactly one point, and that is actually the line S here, which goes through all 3 points, because this point here has to go through all 3 points, so it is exactly that line that goes through all those 3 points here. Yeah? So this point here has a specific alpha, so a specific normal vector, and a specific delta. So here, so this actually represents exactly this line here. Yeah. So summing up the properties, so a point in the data space, a point in the original data space, is mapped to a sinusoidal curve in the parameter space, just because it's a combination of sinus and cosine operations on the angles of the normal vector. Yeah? So a point, original point in the original data space is mapped on a sinusoidal curve in the parameter space. So for example here, the red one here is the sinusoidal curve for P1, and for P2 it's the green one here, for P3 it's the blue one here. Now it's a three-dimensional example. Yeah? So a point in the parameter space, a point here in the parameter space, is one hyperplane in the data space. Yeah? And if it's on the red, on the blue graph here, on the blue function here, it goes through P3. If it's on the red one here, it goes through P1, and if it's a green one here, it goes through P2. And then now the interesting point is that points on a common hyperplane in the data space, so what we call a correlation cluster, by the way, so those points here, those 3 points, are on a common hyperplane in the original space, and that's what actually we want to search for. Yeah. So points on a common hyperplane in the data space are sinusoidal curves that intersecting at exactly one point in the parameter space. And well, with some fantasy here, just believe me, those 3 graphs intersect so there's a pairwise they intersect on many points, but all those 3 intersect in exactly one point, which is this one here, and that has one specific alpha 1 and alpha 2. So now the normal vector has 2 angles. So those are the angles of the normal vector and the specific delta, and those 3 values here actually specify exactly this hyperplane where all those 3 points are located on. Yeah. So what we need to see, or what we need to look for if we look for clusters, are intersections of sinusoidal curves in the parameter space, because those are hyperplanes that accommodate the corresponding points in the data space. Yeah? So now the idea is not apply PCA or something like that, but apply the Hough transform. So transform each point into the Hough space, yeah? And then look for intersection points. So points where a lot of curves intersect, they are clusters.